Welcome to Chapter 19, Section 2. We're going to talk about how we get magnetism from electricity. So what we're going to do is we're going to describe the magnetic field produced or made by a current in a straight conductor and in a solenoid. And then we're going to use something called the right-hand rule to determine the direction of the magnetic field in a current-carrying conductor. So what we're learning is the fact that electric current through a wire can create a magnetic field, okay? So it doesn't just have to be like a solid magnet like this with a north and a south, okay? We can also get a magnetic field from wire and current flowing through. So anytime you have a long straight wire like these, okay, the magnetic field created is cylindrical, okay, meaning it makes a cylinder shape, right? Something like this. Magnetic field around the wire. Okay, and so these pictures are just showing that. So here, like we've done before, these are little filings. Okay, and you can see the way that they all line up with the magnetic field as the current flows through this wire. And here too, we're using compasses to see that it creates this circular, okay, and then in 3 dimensions, cylindrical field around our wire. So the way that we talk about the direction of the magnetic field, okay, is we use something called the right-hand rule. And you must, of course, use your right hand. Okay, if you use your left hand, it will not work and you'll get the opposite signs, okay? So we use this to determine the direction of a magnetic field created by a current-carrying wire. So what you do, like in this picture, is if this is the wire, okay, then you'll have the current through it and you point your thumb in the same direction, okay? So your thumb points the same way. Okay, then what happens is the direction that your fingers curl around here, right, you can see matches the direction of this magnetic field. And that's the way that the magnetic field goes around a current-carrying wire. Okay, so it's really hard to draw this in 3 dimensions, so we have a few tools to help us do that. Okay, and this is from your textbook, okay, and it's the conventions, meaning just the way that we draw the magnetic field, okay. So let's say we have a wire, okay, right, and the current is traveling through in that direction, okay. So if we use the right-hand rule, and I want you guys to actually do this while you're watching the video, so point your thumb in the direction of it, and you'll see your fingers, if they're coming behind that wire, will come out towards you. Okay, and they will come out towards you on this side of the wire. So if you'll see here, it says out of the page, you draw a circle. So what we're going to do is we're just going to put some little circles on this side of the page. Okay, and that means the magnetic field is coming towards you. Okay. Okay. Now, if you think about it, to get your hand around that wire, you had to push your fingers into the page before they came out. Okay. So what we do then is anytime you'd be going in on this side, okay, and anytime we do into the page, we draw an X. So I'm going to draw X's on this side, okay, and they should match the circles that are sitting on the other side, so the same number, okay. So what this tells us, okay, is that you can imagine that the magnetic field goes back and around and then comes in front of the wire like that, okay. So that's what these symbols tell us. If the current is in the plane of the page, meaning it's parallel to the page, then we would just draw an arrow in the direction of it. Okay. So let's just double check this and we'll try one more. Now we've got a wire going down. Okay, so the current is coming in this direction. So put your thumb in that direction too, and notice how your fingers curl around. Okay. Now your fingers should go into the page on this side. So into the page we draw some X's, okay, and then they will curl around and they will come out of the page on this side here. So we will draw corresponding circles to go with our X's. So that's the simplest way we can draw magnetic fields, and we will get the chance to practice this in class. So if we use this idea and we take our current, and instead of just having it in a straight wire, we put it in a loop, we can still use the right-hand rule to figure out the direction of our magnetic field. So if you imagine, especially on this side, right, your thumb should be pointing out towards you because the current is following this area, okay, and so it's coming towards you out of the page, and so you can see your fingers should curl around in the same direction. okay? And over here it would be going away, and so you end up with the curling going this way. And so you get this effect of kind of this looping around that is going on. Okay, now this might begin to look a little bit familiar, and I want you to think about that. Okay, so if we do this and we have a loop, and here's our loop, and this time it doesn't have anything bringing it in, okay? But you can kind of imagine, remember, the arrows always go from north to south as they come out. So don't worry about the inside, right? But this arrow comes out, and it goes around to the south, right? And this one's coming out, and it goes around to the south. This one comes out of the north and goes around to the south. So this begins to look like a bar magnet. Right, so you could kind of imagine I could draw our bar magnet here. That would be our bar, and then our magnetic field is doing just what we saw earlier, right? And it would be doing the same thing on this side. Okay, so it's beginning to look like a bar magnet. So instead of just one loop, okay, maybe we take many loops. Okay, we get something called a solenoid. Okay. So when you put many loops of insulated wire together, and it does need to be insulated, okay, you can create an effect just like a bar magnet, okay? So this is what we call a solenoid, right? So you can see the magnetic fields here look almost the same for them both, okay? So solenoids effectively, meaning in practice, have north and south poles, okay? And if we keep adding loops, the more loops we have, the stronger the magnetic field that we get. So let's go back and think about what we learned last time, okay? Why are atoms magnetic? This should be a question, okay? So I want you to think about the definition of current, right? Well, the definition of current is just moving charges. So if you think way back to chemistry, right, we have the model of the atom where we have the nucleus, right, sitting in the middle, and around it, we've got all these electrons moving around, right? Okay, and they don't go exactly in circles, but they are traveling around. So even if we have just one electron moving, we have a current, okay? So if we have a current moving, guess what happens? Okay, we get magnetic fields. And that's how we get this domain that we were talking about in the last video, okay? So since electrons essentially travel around atoms, we can imagine they are traveling in the path of a loop. Okay, we don't always know that. That's why we're imagining this, okay? But what that looped path does is it creates a teeny tiny magnetic field. Okay, and so what happens is you get effects like this where you have things like what we talked about before, iron, nickel, cobalt, right? The others, all the atoms create tiny magnetic fields, but only in these ones can they like line up clearly. So that answers how we had those little tiny domains of magnetization. So that brings us to the end of this section. You'll get a chance to practice this in class, and I will see you guys there.